to talk about shadowing and diffusion in Hamiltonian systems.
All right, thank you very much. So basically, I will talk about three models for Hamiltonian instability. One will be a perturbation of a geodesic flow, another one would be the large gap problem, and the third will be the spatial circular restricted three-body problem. And everything sort of goes back to Poincaré, who asked the question about the long-term behavior of a nearly integrable system. And well, it is well known, like you take a system like this, and if you set epsilon equal to 0, then the system is integrable, which means that you have permanent stability. If you have epsilon sufficiently small, and you have some smoothness and non-degeneracy condition, then KM theorem apply, and you have that most tori will survive the perturbation from the integrable case. And if you happen to be on the tori again, you are going to have permanent stability. The question is what happens if you are outside of the tori. So if the system is a 2-degree of system, so the energy hypersurface is 3-dimensional, and the 2-dimensional KM tori separate the energy hypersurface in connected components. So again, if you happen to miss the tori, you are still going to have a permanent stability. You are stuck there forever. And the question is, if you have, actually this should be strictly greater than 2 degrees of freedom, then you have the possibility of instability. So the question is whether this is always the case. So besides historical reason, these type of questions are important for applications. And sometimes in applications you want stability, let's say for plasma confinement devices. But so for some other types of applications, you want instability, let's say for low energy space mission. And here I like to mention that probably the first space mission, successful first space mission that used Hamiltonian instability was the Hitten mission to Moon in 1991, based on the weak stability boundary introduced by Belbruno. So here you have like some sketch of that mission. So oops. Okay. 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 So in the center there is the Earth, and the small circle is the trajectory of the Moon. So the idea for this mission to take the spacecraft from the Earth of the Moon was actually to make a very large detour using this concept of weak stability boundary and return to the Moon for a ballistic capture. So this very practical idea, actually we are going to see it for again and again. So it sort of turns out to be the case that sometimes for low energy space mission, if you want to take the most economical route, you have to make a large detour. So it turns out that instability, Hamiltonian instability, seems to be a rather typical type of phenomena. And this goes back to a question by Arnold, saying that generic, well, informally, generic perturbations of integrable system have trajectories that visit a large part of the phase space, and also you expect to have symbolic dynamics. So according to a classification proposed by Kierkegaard and Galavotti, one can sort of consider 2 types of system. A priori stable system, for which the unperturbed system can be expressed in action angle variables only. So this is like the harder problem. And the a priori unstable case, which is less hard, let's say, when in the unperturbed system you already have some hyperbolicity. And there have been lots of works and results. So here I'm just going to mention a few, and I apologize if I'm going to miss many others. So there are variational approaches, and particularly, so most of these results are actually for the unperturbed problem, and John Mather have results actually for the a priori stable case, which were announced and presented and so on. And these are based on variation. Some approaches are based on variational methods. There are also geometric approaches and topological approaches. And a sort of related problem is to estimate the diffusion times. And there are, again, various settings for the estimates on the diffusion times, and lots of research in that direction as well. So I want to quickly go over Arnold's original example from 1964. So this is basically a mechanical system consisting of a rotator, a pendulum, and a small coupling. And the coupling is of a very special type. Let me also remark that this is a two-parameter problem. So the perturbation is time dependent. So one of the standard things is to make it time independent by introducing an extra variable. And one can get like a 3 degree of freedom autonomous Hamiltonian. So then one analyzes what's going on in the absence of perturbation, let's say epsilon equal to 0. And what happens if you introduce a small perturbation. So when epsilon equal to 0, you can distinguish geometric objects that organize the dynamics. So you have a 4-dimensional manifold which has stable and unstable manifolds that coincide. If you cut this by a surface of section, by an energy hypersurface, inside the energy hypersurface you find a 3-dimensional normally hyperbolic invariant manifold. This, of course, has stable and unstable manifolds. The 3-dimensional one is filled with invariant tori. So the invariant tori themselves have stable and unstable manifolds, and they coincide, and we're pretty much like in that picture. So you have a cylinder of periodic orbits, and stable and unstable manifolds coincide. And then you make epsilon very small. And actually, you have to make epsilon much, much smaller than the other parameter mu. And what is important in the Arnold example is that the perturbation is chosen of a very special form, so that when the perturbation kicks in, the cylinder of tori survives, and moreover, all of the tori are surviving the perturbation. So all remain pretty much the same. Well, the only thing that it happens is that the stable and unstable manifolds of nearby tori start to intersect transversally, and then you can move from one tori to the next, to a nearby torus using a heteroclinic connection, and move again and move again. So you can link nearby tori through heteroclinic connections and obtain a transition chain. And then you use some sort of easy topological argument that this chain of geometric objects is shadowed, is followed by a true trajectory. So the really special thing about Arnold's example is the perturbation. So the perturbation is very special, it's not generic. So the question posed by Arnold conjecture is whether you can do this in some generic sense. So what happens, so now I'm going to sort of switch that for let's say we have only one parameter, one perturbation parameter. So I'll be more precise a little bit later. So if you'd have just one perturbation parameter, then what typically happens when you apply the Km theorem, you are creating gaps between the Km tori. The largest gaps can be of the order square root of epsilon, while the splitting of the stable and unstable manifolds is going to be smaller of order epsilon. So it is possible that you can travel, you can still create these transition chains, but at some point you may reach like a gap where given by the failure of the Km theorem, and you cannot really, you don't know really how to cross that gap using this Arnold's mechanism of Arnold. So the question is, the large gap problem is how to do these two things together follow the transition chains, and when you reach the gap, cross those gaps. So I would like to discuss 3 models for this more general problem. So one will be perturbation of a geodesic flow. So the result will basically say that if you have a geodesic flow on a manifold with some generic Riemannian metric, and you apply a time periodic perturbation, you will get trajectories whose speed energy goes to infinity in time. The second one is the large gap problem. So basically, if you have a pendulum rotator system as before, and if you put a small generic type of perturbation, you expect to find trajectories for which the action variable changes order 1 over time. And the third problem, it's the spatial circular restricted 3-body problem for a very concrete choice of primary. So we're going to talk about the Sun-Earth system, and let's say the motion of a satellite with respect to this system. And we want to show that there exist trajectories that increase or decrease, as you wish, the out-of-plane amplitude with respect to the ecliptic as much as you want. So this is a picture of the third situation. So you do not see, so this is like a picture from the top down, so you don't see actually the change in the out-of-plane amplitude of the ecliptic, of the trajectory. So I'll show this in a different picture. What I want to emphasize here is, like, if you want to achieve an increase or decrease of out-of-plane amplitude around the libration point, which happens here, you have to take a large detour. So it's the same theme that we've seen in Bell-Bruno's trajectory. So basically, you have to take this is the libration point of Sun-Earth system. So this is where Earth is. So you have to make a turn, a full turn about the Earth, and come back by the libration point. So so I will sort of describe in some detail one example at a time. So the first example is the perturbation of the geodesic flow. So it was first shown by John Mather in a preprint that you have a geodesic flow on the 2-dimensional torus, and if you apply some generic type of perturbations that are time periodic, you find trajectories whose speed energy goes to infinity in time. And then there's some, Deav and Sarah show the same result when you take any manifold, but with a generic metric. And you can do time periodic perturbations, but you can also do quasi-periodic perturbations. So the result that I want to show today is somewhat more general result. So when you do the coupling of a geodesic flow on a manifold with some external dynamical system, which in the previous example was the quasi-periodic motion on the tori, and on this dynamical system you have to assume some sort of recurrence condition, and you can essentially prove the same result. So the point would be that the perturbation does not need to be quasi-periodic. It can be of a general time. And again, we are going to find trajectories whose energy grows to infinity, and we are going to estimate the speed of diffusion, and we are going to show that the speed is optimal. I mean, we can achieve optimal speed. And we do this using geometric and topological methods. So this is the setup. So you have a manifold with a metric. So for the topological methods, we need low regularity. And you have the geodesic flow, which can be viewed as a Hamiltonian flow given by the metric. And now we put the external dynamical system. So you have another manifold and some flow on that manifold given by a vector field. And V represents like the coupling, or you may wish to think of external potential that is like time dependent. So you have a new parameter and time dependent Hamiltonian, which is the original Hamiltonian, the integrable one, plus the coupling between So this is like the potential part, and this is the influence from the external dynamics. So the assumptions on the original manifold on which you have the geodesic flow is that you want to have a closed geodesic which is hyperbolic for the geodesic flow. And this geodesic should have stable and unstable manifolds who intersect transversally for a fixed energy level. And then the recurrence condition is that if you are in the external manifold on which you have the external dynamics, whenever you have an open set U, there exists a finite time such that if you push this open set on the whole manifold, you are going to cover the whole manifold in finite time. So we believe, I mean, this can be made even into a weaker assumption, but let's say for the purpose of this talk, this would be enough. So the idea is that you should be able to go anywhere inside the external manifold. And let me remark.
Sorry. Can we go back to the last slide for a moment? Can you tell how exactly these two systems are coupled?
So basically, you have this function that is defined on, so which is like a potential.
Q and P are in M and in N?
So yes, so Q and P are in M, and you also have on the other manifold N, you have an external flow, and you let this external flow to influence.
Oh, it just influences it.
Yes.
Outside.
Yes. So this happens outside. So it takes like a potential.
So theta 0 is
some initial condition on the external manifold. So if I cover this, so basically I have a time-independent potential. But now I let this potential to vary in time, and I let it vary according to some.
So really, you're just adding a time-dependent potential.
Exactly.
But it comes from.
So let me go back to the assumption 1 and 2. So the existence of a hyperbolic orbit who has stable and unstable manifolds that intersect transversally. So this was shown to be generic by Contreras. So that's a generic condition. So it's a C2 generic for C infinity Riemannian matrix. So so under these assumptions, and for some generic conditions on V, that on this potential, so the generic conditions, I'm not going to list them, but I will have to say that they are explicit conditions, so conditions that one can verify. So one can take this function V and actually check whether it satisfies these conditions or not. So under these conditions, there exist solutions for which the energy grows to infinity in time, and it grows like the time does. And it can be easily proved that this is optimal. So the point is, we can show that there exist orbits that achieve this optimal growth. And of course, every time I'm going to have a result like that, due to the geometric topological nature, subsequent will be there exists symbolic dynamics. So the second one, it's a mechanical system consisting of a rotator and a pendulum and a small time-dependent perturbations. And by the rotator, we mean that this quantity, this Hamiltonian, satisfies like a non-degeneracy condition on some interval. And the potential here, I mean, this is really supposed to be like the usual pendulum, or you can say that something more general, that it's a potential that has a non-degenerate global maximum. So subsequently, we have homoclinic orbits associated to that. So basically, the result is that under some conditions on the perturbation H, which are again generic and verifiable, there exists a small epsilon such that for all epsilon up to this cut-off value, and for every choice of, and for every interval in the action direction, I minus, I plus, with some restriction within some domain. So there exists a trajectory which at the beginning it has the action value less than I minus, and at the end has the action value bigger than I plus. And these quantities, I minus and I plus, do not depend on the size of perturbation. So this trajectory is of order 1 with respect to perturbation in the action variable. And we can also prove, but this is a rather work in progress, that we can achieve this in optimal time. And the optimal time was conjectured by Loschak to be 1 over epsilon ln of 1 over epsilon. And this is like a short, let's say, a movie of how this really happened. So what you see is the phase space of the rotator. You do not see the pendulum, and you let a bunch of initial conditions involve. And you see that sometimes if you let them move at random, sometimes they move forward, sometimes they move backwards, but they manage to travel a long distance. Well, of course, one of the key features of this is that this is an extremely slow process for epsilon small. So in this animation, epsilon is quite large to make it work. So the third model is the spatial circular restricted three-body problem. So the idea is that you take the two masses, like Sun and Earth, and you consider the motion of a third particle of infinitesimal mass with respect to the two primaries. And the assumption is that the infinitesimal mass does not exert any influence of the primaries. So the primaries are let move on circular orbits about their center of mass. And one usually studies this in a co-rotating frame. So you look at the Earth and the Sun in fixed position on the horizontal axis, and you only track the motion of the infinitesimal particle. And this can be described by a Hamiltonian, and there are 5 equilibrium points, 3 collinear, 2 forming equilateral triangles with the masses. The collinear ones are of center, center, saddle. And we are going to focus on L1, and by our convention, L1 will be the libration point in between the primaries. And there is, if you restrict to an energy manifold, which is 5-dimensional, inside this manifold, you can find a normally hyperbolic invariant manifold, which is 3-dimensional and contains many invariant tori. So I'm a little bit vague here in terms of when does it happen. So usually in celestial mechanics, well, until very recently, the only rigorous things that you can say are for extremely small mass ratio and for energy values very close to L1. But now with the techniques from symplectic topology, there are positive results beyond these boundaries. So, so these are the liberation points. So what we want to say, and this is a semi-numerical result. So if we have inside the 3-dimensional normally hyperbolic invariant manifold, if we give ourselves a sequence of tori and a small epsilon, then there is a trajectory that moves from the epsilon neighborhood of one torus to the epsilon neighborhood of the other torus in the prescribed order. So basically what you see here is like a surface of section, and the cuts are the circles. So you can imagine that you can jump back and forth between these tori any way you want. But the picture here is a little bit more complicated. So this is an energy level where the normally hyperbolic invariant manifold is sort of destroyed. So, I mean, if you are close to the energy level of the liberation point, you would only see this part, if you push it further, you start to see some stochastic region and some other type, like a secondary type of tori. So the question is whether you can do more than that. And we believe that with some of the techniques in this paper or with some other methods, we can actually jump from here to here and do anything you want. Yes?
The central one is libration point?
Yes, so the central one corresponds to the libration point. So the central one, I think, corresponds to the vertical orbit, and the other one are. So this result is, let's say, semi-numerical, which it's a mysterious term, but I will try to say something about it. But we can make it an analytical proof using the paper and the techniques in Libre, Martinez, and Simo from 1985. If you let the mass ratio being very small and you stay very close to the energy of the libration point. And I'm just mentioning here a couple of other results about diffusion. I mean, this is a phenomenon, whether you want to call it diffusion or not, but it does use the Arnold's mechanism of instability, the original mechanism of connecting invariant tori with heteroclinic connection. And these mechanisms have been exploited in some other papers, and I'm mentioning here just a couple of them. And a possible application for this type of result, I mean, this is a very concrete type of system. So one can actually take the motion of a satellite about the libration point, and you can start from a nearly planar motion and progressively incline the orbit of this trajectory up to some angle. But every time you have to incline it a little bit, you have to take a large detour around the Earth. So it's a time-consuming process, but that's how Arnold mechanism is supposed to be. So let me say something about the methods that we are going to use. So some of the methods are pretty standard. So we are going to use normal hyperbolicity. So for example, for the pendulum rotator system, if you, so you add an extra variable symplectically conjugated with the time, and you take then an energy hypersurface and the first return map to a surface of section, you can reduce the problem from a flow to a symplectic map. And for the map, you are going to find first, for the unperturbed system, a normally hyperbolic invariant manifold. And then when you add the perturbation by standard Puy and Schub or Sacker-Fenichel, the normally hyperbolic invariant manifold survives the perturbation, and you work with this object. And you are going to have you are going to think about two types of dynamics. And one is the dynamic restricted to the normally hyperbolic invariant manifold, which is of twist type, and then outer dynamics, which I'm going to discuss next following the heteroclinic connections. So to have like a very systematic way for following this heteroclinic connection, one can use the scattering map, which was analyzed by Del Sams, Deav, and Serra in several papers. So essentially, you fix yourself. I mean, okay. So first of all, you need a homoclinic intersection of the stable and unstable manifolds, which you can usually get through Melnikov theory. In the geodesic flow, you sort of get it for free. So this already has homoclinic intersection. And then you fix a homoclinic manifold, and then you choose a point on the homoclinic manifold, and due to the normally hyperbolic invariant structure, this point is on a unique unstable fiber, and let's call the foot point x minus, and on a unique stable fiber, the foot point is x plus. So the scattering map is really x minus goes to x plus. And the scattering map is computable. So this is the main quality. And well, let me just make a quick remark that this is not a dynamically defined map. So there is no trajectory that goes from this point to that point. What it really happens is that if you follow this point, for example, the base point will move. So you'll approach asymptotically the backwards image of the foot point, and if you move this forward in time, you will approach asymptotically the forward image of that. So, so the point in all of this example is to compute the scattering map using, let's say, Melnikov theory up to some. And basically, you want to prove that in all of these examples, using the scattering map, you can increase the action variable by, let's say, order epsilon. That would be good. So now we are going to refer to the inner dynamics. So the inner dynamics is given by an exact symplectic monotone twist map, and we are going to think a little bit about the obstacles that can show up, and so you want to move inside the. So in our case, this normally hyperbolic invariant manifold for the map will be always two-dimensional. So the discussion is in 2 dimensions only. So the obstacles that you can get are invariant tori, which if they exist, I mean, I'm talking about primary tori, which are have non-trivial topology, as opposed to secondary tori, which can be shrunk to a point inside the annulus. So these are Lipschitz graphs. And one of the oldest results is Birkhoff connecting theorem. So if you have topological transitivity on the boundaries of the, okay, so what is the object here? So the object here is a Birkhoff zone of instability. So Birkhoff zone of instability, it's a region between 2 primary tori so that there is no other primary torus inside. So there is no obstacle. And then Birkhoff showed that if you choose a point on either boundary and the neighborhood of each point around each point, so then there is a trajectory that goes from the first boundary to the second boundary. You need topology in the classical result. You need topological transitivity to do that. Otherwise, you can do it without topological transitivity, but you go from a whole neighborhood of T1 to a whole neighborhood of T2. So then inside the Birkhoff zone of instability, we are also going to have Aubry-Mother sets, which for us are going to be monotone F-invariant sets of given rotation number. And minimal here will be in the topological sense, so not in the variational sense. So the approach will be topological, so no variational principle. So then between within the rotation interval, you can find an Aubry-Mother set for each rotation number. And if you give yourself a sequence of rotation, a B-infinite sequence of rotation numbers within the rotation interval, then there is an orbit that goes epsilon close to each of these Aubry-Mother sets in the prescribed order. So you have symbolic dynamics. If you use topological methods, you can get a result which is very similar. It was proved by Hall, but except that you are not getting close in this sense. You are not getting epsilon close to the Aubry-Mother sets, but you follow the angle variable for. So in the sense of ordering, so you are going to move in the same way as the points on the Aubry-Mother set do. And the last ingredient is a topological method of correctly aligned windows that goes back to the early works of Conley, Easton, and McGehee. And basically, a window is just a homeomorphic copy of a multidimensional rectangle, and one window is correctly aligned with another. If you take the first window and the image of that is crossing the second window in some sort of non-trivial way. And now you may ask what is non-trivial. So it can be expressed. So in the picture, it has to go all the way through, and then you can express this using like Brouwer degree. So it has to be like a robust type of crossing that is invariant under small deformations. And one of the nice quality of these windows is that if you have a B infinite sequence of them such that each window is correctly aligned with the next, then there is a trajectory that follows this sequence of windows in the correct order. So you can use this method to find symbolic dynamics. And the second nice thing about that is that the correct alignment is robust, so you can implement it numerically and use it in like computer-assisted proofs. So now I want to say a few things, a few words about each of these proofs. So the techniques here are sort of pretty standard, so I'm just going to go quickly over them. So you fix one of these closed geodesics and homoclinic orbits. So I'm going to the geodesic flow, right, with the external perturbation. So I want to prove that there are trajectories for which the energy grows to infinity. So you fix one of the closed geodesic that is assumed to exist for some energy level, and due to rescaling, you have a closed geodesic at any energy level, and you have homoclinic orbits at any energy level as well. And if you start with some high enough level of energy and go up, take the union of the product of these closed geodesics times the n, which is the external dynamical system, then you are going to get a normally hyperbolic invariant manifold for the Hamiltonian flow of the coupled system. So, and the stable and unstable manifold, so this is a decoupled. When epsilon is 0, the system is decoupled, so basically the stable and unstable manifold of these are formed by the stable and unstable manifolds of the closed geodesics times the external manifold. And so is the homoclinic manifold. So then you introduce a small parameter. So you want to rewrite this problem as a small perturbation of an integrable problem. So this is 1 over square root of the energy. And then you do a rescaling of the coordinates and of the time. And in the rescale coordinates, you are going to get the original problem written as a small perturbation of an integrable system. So when you do this in the external, for the external dynamical system, this becomes like a slow motion. So you have a fast motion on the original manifold and a slow driving force outside. So then, so there you can put action angle coordinates, and the next thing you do, you use averaging, like you take 2 steps of averaging, and then you can compute what happens to the energy to the level of the averaged action when you apply the map. So it turns out that you are able to preserve the level sets of the action variable up to order epsilon to the 4th. So this is something that follows from the computation. And when you compute the scattering map for this, you realize that through the scattering map, you can make changes in the action variable of order epsilon cubed. So the key point being that the jumps are bigger than the error that you accumulate when you use the inner dynamics. So when you use the inner dynamics, the error is epsilon to the 4th. When you use the outer dynamics, the gain is epsilon cubed. So you can make progress. So basically, you sort of move from one action level set to another. And in these small steps, one at a time, you can sort of change the action variable, and if you change the action variable, what you actually change is also the energy of the system. So, and if you do careful estimates, okay, so now you want to say, put some quantitative estimates on that, so you have to localize the trajectory better. So one way to do it is using this topological method of windows. So imagine that you start with a pair of rectangles that are correctly aligned. So one is crossing the other in the non-trivial way by the homoclinic manifold. So this corresponds to some action level set, and this corresponds to some other action level set. So when you move this down, what happens is that when you depart, the exit-like direction, the stretching-like direction, is the direction of the angle. And when you arrive, the stretching-like direction is the direction of the action. So you have this switch when you use the windowing method, and you are going to use this switch. So from going from this level set to this level set, you use the heteroclinic connection, and what happens is you get a switch in the stretching-like direction. Now you want to go from this to another level set. You are going to use the inner dynamics, and the twist property will help you to sort of recover to the original stretching-like direction. So it's a two-step maneuver. So first you get the direction sort of reversed, use the twist, and you get back to the original choice of directions. And so if you create these windows and you put careful estimates on the sizes of the windows, then you can actually prove that the trajectories that follow these windows change the energy like the time. And this is optimal. You cannot go faster than that. So this is basically the first result on the perturbation of the geodesic flow. And the novelty here is that instead of periodic or quasi-periodic perturbation, you have some external dynamical system that sort of takes a potential and it messes it up in time. So this is what happens when the second step, when you use the twist map to recover the original direction. So when you use the twist map, you are going to, you have this rectangle. The exit direction is the vertical one. The one that you want to hit is horizontal one. So if you have some control, then you are going to cross it in the correct way. And the control comes from the estimates that you make on the inner map in the average action angle coordinates. So now this is the large gap problem, and first I'm just going to say that this is on this slide is the approach of Der Sams, De Have, and Sarah. So when they reached the large gaps, the idea was to find other objects to connect one side of the large gap to the other. And the objects that they used were secondary tori and hyperbolic periodic points and their invariant manifolds inside the annulus. So then they were able to construct transition chains like Arnold's made of primary tori, but they were able to link them with the secondary tori or with the stable and unstable manifolds of hyperbolic periodic points. And if you use the topological argument, you can do this without the KM. So you don't really, because of the robust nature of the windows, you don't really need to know that these are invariant. You only need to know that they are almost invariant for some long enough time. So you can use that to avoid KM, and avoiding KM means that you need lower regularity conditions. So for example, in this work, in the original work, I think the original functions were supposed to be something like class 100 in terms of differentiability, or 200, something like that. And with this, we can go to C4. So now I want to show you a different mechanism, which is much more topological. And the idea is that if you find somehow some good invariant objects that organize the dynamics, and even if the gaps are pretty large, then you don't really need to worry about the size of the perturbation. Well, this is a question like the chicken and the egg. So how can you make sure that these geometric objects really exist? So, but let's assume that they exist, and let's assume that you get them from perturbation theory, and I mean you have a small perturbation to begin with, and you have these objects. And these objects are sort of very similar to one that you've seen before, except that we don't have secondary tori and we don't have hyperbolic periodic points, and they are invariant manifolds. So you have the transition chains, more or less, but when you reach the gap, then you are not interested what are the objects inside the gap. But the price that you have to pay is that you have to go to the edge of that gap. So you have to move the transition chain until you cannot push it any further. So the idea here is that you model the large gaps by Birkhoff zones of instability, and you use the transition chain to get to the boundary of these Birkhoff zones of instability, and then you use something like either Birkhoff connecting orbits or Mather connecting orbits to cross these Birkhoff zones of instability, and then go to the next transition chain, and so on. So these are a bunch of hypotheses here, but this hypothesis, so the first group of hypothesis really says that you have a transition chain, and these chains are pretty much like KM tori, so they have topological transitive dynamics, and each torus can be approximated from both sides by other tori. And at the boundary, you have basically no assumptions there, except that you can get there using the transition chain. And now inside each Birkhoff zone of instability, so your first objective would be to move along the transition chain and then cross the gaps. Fine. But let's say that you throw in a finite collection of Aubry-Mather sets inside of each Birkhoff zone of instability, and you want to visit every single one of them. Yes, you can do that. So that's on the last line here. So, and for this argument, all of these tori in the transition chain are supposed to be only Lipschitz, so the regularity it's pretty low. So, I mean, how does one apply this? So, for example, if you go back to the model considered by Der Sams, Dehav, and Sarah, all of these ingredients come from applying perturbation theory. And you know, I mean, one of these arguments was that you can go from a primary torus to a secondary torus, so you can get from this transition chain inside the resonant region. But if you can get there through the scattering map, you can also get the boundary of the Birkhoff zone of instability, wherever that is. So this approach does not require you to localize where exactly is the Birkhoff zone of instability and what is the dynamic of the Birkhoff zone of instability. But the idea is that can you go there? And if you can go farther, it means you can go even to the boundary of the Birkhoff zone. To make this argument work, so you have to combine the inner dynamics with the outer dynamics, and we wanted again to use correctly aligned windows, so it had to be a pretty topological approach for that. So this is the topological version of Mather's connecting theorem. So you have a finite, now we have to go, we are going to consider only finitely many Aubry-Mather sets because you want to actually jump to the boundary of the Birkhoff zone. So you take finitely many of these Aubry-Mather sets, and there is a trajectory that starts very close to the lower boundary of the Birkhoff zone, then visits each of these Aubry-Mother sets, and then ends up close to the upper boundary of the Birkhoff zone. And by the fact that this orbit visits the Aubry-Mother set is that for any prescribed duration of time, the trajectory stays between 2 points of the Aubry-Mother set. So it moves like with the same rotation number, like for a finite duration of time, which is as long as you want to prescribe. So, so these are some remarks that I think I already mentioned. So you don't need to know. I mean, this Birkhoff zone of instability should exist, and you don't need to know where they are, but you need to know that you get there or even beyond. So if you have these objects, you don't really need to know that the system is close to integrable. So you sort of freeze a perturbation, you look at the geometry, and if you see these geometric objects, then you don't really care what was the size of the perturbation, whether the Birkhoff zone of instability is rather large, you're going to cross it. So basically, there are two results that are very related, and we need it for crossing this Birkhoff zone. So the idea is that go back to the Birkhoff connecting theorem. You remember that given a prescribed neighborhood of a point to the lower boundary and the prescribed neighborhood of a point on the upper boundary, if you have topological transitivity, then you can go from one boundary to another. So in this case, we are saying we don't really need topological transitivity. We can do it anyway. So, and this is, well, just some cartoon. So this is the original neighborhood that you want to get there, and this is already the first iterate of that. And in this case, it takes just a few of them, and you reach the upper neighborhood. And the second proposition is that if you want to do this with no assumption on the dynamics on the boundaries, but you want to visit a finite collection of Aubry-Mother sets, you can do it again. So probably I'll just say a few things about the first proof and 2 words about the second proof. So it's a Jordan curve theorem type of proof. So assume that this is your original boundary, and you have another boundary on the top that I'm not showing. So and you take this neighborhood of a point, and here you put 2 Aubry-Mother sets that are sufficiently close to this boundary. So first you take this neighborhood and you iterate it until you make it go like this through a point which is way beyond these Aubry-Mother sets. So if you go beyond that, you have to pass through one hole here and one hole there. But now if you take this neighborhood and keep iterating it, so these Aubry-Mother sets will have different rotation numbers, and at some point the gaps will sort of shift apart. So a higher order iterate of that will sort of go through a gap on the left and through a gap of the right. So this will create what it looks like an arch. So what you get like some sort of neighborhood of some points on this Aubry-Mother set. And you have a similar picture on the top. Now, a Mother connecting theorem says that you can go from this neighborhood to that neighborhood, which means that there is a point on the boundary of this arch that goes on the boundary of the other arch, but the boundary of this arch is actually something that corresponds to the original neighborhood. So tracking back your argument, there is a point here, actually on the boundary, that goes on the other neighborhood on the boundary. So if you want to shadow a prescribed sequence of Aubry-Mother sets, the argument is a little bit more involved. So, but really what you have to do is go back to the topological argument of Hall. So it appears in an article in a Banach Center publication and also in the book by Meyer, Hall, and Affin. So you construct these so-called diagonal sets, and he uses these diagonal sets to find the trajectories that follow these Aubry-Mother sets for a prescribed number of iterations, and then they jump to the next Aubry-Mother set for another prescribed number of iterations, and so on. So you sort of have to take the first argument with the second argument, combine them somehow, make it work, and that means you go from nearer the boundary to near the other boundary and visit what you want in between. So I'm going to sort of skip through that. So the pictures are just showing that you have a constructive procedure, which is step by step. So you make selections at each step. Maybe the neighborhood that you iterate is not good enough. You shave it, and you find a recursive argument that does this for a finite time. So then the last part of the argument is you have the transition chain, and you want to connect using windows the trajectories that move on the transition chain with the trajectories that cross the large gas through this argument. And again, there is some, let's say, a little bit of acrobatics that you do with these windows to show that you can actually do it. So what you obtain, let's just say, if you take the model of that was analyzed by Del Sams, Gidea, and Serra, you use their estimates, but you obtain a diffusion mechanism that is different. So when they reach the large gap, they kept using the outside dynamics. But when we reach the Birkhoff zone of instability, we used like the inner dynamics. So this is similar to the variational methods. So at least the paper of Cheng and Yan are sort of obtaining this type of orbits. But since we do it without variational arguments, we have a little bit more relaxed assumption on the unperturbed Hamiltonian. So again, I'm going to skip here some very delicate operations and I just want to say a few words about the last problem. So this is a very concrete problem. So one of the objectives of this was, well, not only the result itself, but the method. And the point was whether you can apply this method to concrete system, and concrete would even go as far as through computer-assisted methods. So when you take the Sun-Earth system and an energy level that is not very close to L1, so you can do computation using normal forms up to an incredible order of precision of the normally hyperbolic invariant manifold and of the tori that cover most of it. So now all of these tools work better with discrete dynamics as opposed to flows. So you take a Poincaré section and you see what happens in the Poincaré section. So this is not a global surface of section, so it's local. So all of the results sort of hold locally. So, and if you have something normally hyperbolic for the flow and you cut it locally, you find normally hyperbolic structure for the map, and this is due to Fenichel.
What was the picture?
This picture?
Yeah.
So this is just a bunch of tori inside the normally hyperbolic manifold about liberation point L1.
And same color means what?
The same color?
All red one torus?
No, so red is one torus, blue is another torus, and this is undefined color. It's this is supposed to be green, so it's a third torus. So numerically, I mean, these tori are two-dimensional in the Poincaré section. In real life, they are two-dimensional, and you want to find the intersection of stable and unstable manifolds of these tori, which are so it's a relatively hard process numerically to find these intersections. So, but once you find these intersections, you can compute the scattering map. So the scattering map is what it organizes the dynamics following these heteroclinic excursions. And now I will show in the surface of section the effect of the scattering map. So in red, it's an initial level, and in green is what happens when you apply the scattering map to it. So at different levels, you see slightly different pictures, but the idea is that you can start somewhere here, and this action variable corresponds to some out-of-plane amplitude, and you can get higher. And it becomes if you want to get very high, it becomes very difficult. So then you can sort of use continuation to thicken these to rectangles, to windows. So this window will go here. So you made some progress. And now from this window, you'll go there. So now how do you go from here to here? You use the inner dynamics, and you may need to spend a lot of time. So this is what happens if you do just 2 jumps. So you spend a lot of time on this tori. So you increase the out-of-plane amplitude from the red to the green, I think a little bit, and then from the green to the blue just a little bit. And this is at the expense of making these large turns about the primary. But even worse, I mean, the really time-consuming thing is to use these inner dynamics until you are able to jump again in the right place. Because sometimes you jump upwards, sometimes you jump downwards. So you don't want to go downwards. So you have to wait until the proper place to jump. So, so what I wanted to, in conclusion, so there are different mechanisms of diffusion, and through the combination of geometry and topology, you can actually combine all of them. So it's nice that you can choose different mechanisms for some period of time and see which one is more efficient, which one you would prefer at a certain moment. And so we did not, everything was done in the a priori unstable case. But so we did not say that, or we did not even attempt to address the harder problem, the a priori stable case. But the advantages of this approach is that the conditions that you need on the system are pretty relaxed. And what we have here, we think that we relax them even more. So we just need some method of jumping, and then some inner dynamics that takes you far. So if probably with a lot less structure, you can prove similar results. And the point would be to reduce the regularity requirements. The system doesn't have to be that close to integrable. It doesn't even have to be, well, really Hamiltonian. I mean, the stable and unstable manifolds, for example, can have different dimensions. And for you, it doesn't matter. So you need, let's say, inside the annulus, you need essentially an exact symplectic twist map. But outside, anything is good. And this allows you to do quantitative estimates on the diffusing orbits. And I sort of showed you a result about the diffusion time for the geodesic, perturbed geodesic model. And we think that we can do for the large gap problem. And I'll stop here.